Drop a simple salt crystal into a beaker of water, and the solid appears to peacefully vanish into the liquid. We naturally view this resulting solution as a simple, static mixture. The microscopic reality is a violent clash of thermodynamic forces. The rigid ionic crystal lattice is actively bombarded and torn apart by a chaotic swarm of polar water molecules. To accurately predict how a solution behaves, we must build the physics of this system entirely from the ground up. We will trace this process through three distinct stages: the thermodynamic vectors that drive solvation, the strict mathematical limits of saturation, and the mechanism by which dissolved particles hijack the bulk physical properties of the solvent. Tracing this progression from individual atomic interactions to macroscopic fluid dynamics yields exact predictive control over both chemical solubility and physical phase changes. The initial phase of dissolution is defined by two competing thermodynamic steps: breaking existing bonds and forming new ones. First, energy is consumed. Tearing apart the tightly packed solute lattice and separating the hydrogen-bonded solvent molecules requires an input of heat, making this initial step highly endothermic. In response, an energetic release occurs. As the water molecules surround the freed ions, they form stable ion-dipole interactions, creating an exothermic release of heat. This bar chart tracks the net energy transfer. For table salt, the energy required to break the bonds is greater than the energy released by forming the new ones. The net enthalpy change is slightly positive. Based strictly on the flow of heat, the salt should remain solid. The dissolution proceeds anyway because it is driven by a different physical property, entropy. Entropy measures the dispersion of energy and molecular disorder. When the highly ordered crystal lattice is destroyed, the freed ions gain access to a massive number of new energy microstates. The water molecules do incur a minor entropy penalty as they restrict their own movement to form organized hydration shells around the ions, but this constraint is highly localized. This equation for Gibbs free energy dictates spontaneity. The large positive increase in the system's total entropy mathematically overpowers the endothermic cost of breaking the lattice apart, driving the final free energy value negative. A solution forms because the chaotic dispersion of the dissolved ions completely overpowers the energetic penalty of tearing the solid apart. This thermodynamic drive to dissolve is not infinite. As more ions accumulate in the bulk solvent, the system approaches a strict limit. Once the concentration of dissolved solute is high enough, the dissolved ions begin reforming the solid. When the rate of precipitation exactly matches the rate of dissolution, the solution achieves dynamic equilibrium. This equation defines the solubility product constant, or KSP. It represents the mathematical boundary of equilibrium. Notice that the solid reactant is intentionally omitted from the expression because pure solids do not dictate equilibrium concentration. This graph maps the limits of saturation. For a specific solute at a specific temperature, the KSP value forms a fixed, immovable threshold line. To track the system in real time, we calculate the ion product. This uses the exact same equation, but inputs the actual concentration of ions present at any given moment. As long as the calculated ion product remains lower than the KSP threshold, the solution is unsaturated. Dissolution continues. When the ion product exactly hits the line, the solution is saturated. The system is locked in dynamic equilibrium. If external factors cause the ion product to spike above the KSP threshold, the solution becomes supersaturated and unstable. The excess ions will immediately and spontaneously precipitate out of the liquid. The saturation point is not determined by the physical volume of the water. It is a strict thermodynamic budget enforced entirely by the KSP equation. While the KSP threshold is fixed, we can artificially dictate how much solid dissolves by exploiting Le Chatelier's principle to manipulate the equilibrium state. The most direct method is the common ion effect. This occurs when a solid is dropped into a solution that already contains a high concentration of one of its constituent ions. Look at the left side of this split screen. The pre-existing concentration floods the product side of the reaction. To maintain the KSP budget, the reaction shifts heavily to the left, drastically reducing the molar solubility and forcing the solid to remain undissolved. We can apply the exact opposite pressure through complex ion formation. Watch the right side of the screen. By adding a highly reactive ligand like ammonia, we introduce molecules that actively bind to the free silver ions via coordinate covalent bonds. This secondary reaction has a massive formation constant. It acts as a thermodynamic vacuum, rapidly draining the pool of free metal ions. To replace them, the primary dissociation reaction is violently dragged to the right, dissolving far more solid than pure water ever could. A chemical solubility is a highly flexible parameter. We can strategically choke the dissolution using common ions, or amplify it using complexing ligands. Once the solute is successfully dissolved, the chemical equilibrium is established. Now, the dissolved particles dictate the behavior of the bulk solvent. This introduces colligative properties. In this macroscopic regime, the specific chemical identity of the solute is completely irrelevant. The only metric that affects the bulk fluid is the Van 't Hoff factor, a pure count of the number of individual particles the solute dissociates into. This cross-section illustrates Raoult's law. The dissolved solute particles physically crowd the surface area of the liquid, blocking solvent molecules from escaping into the gas phase. The rate of condensation from the surrounding air remains unchanged, but the evaporation rate drops. As a result, the overall vapor pressure of the solution is heavily depressed. This drop in vapor pressure directly forces an elevation in the liquid's boiling point. A liquid boils when its vapor pressure equals atmospheric pressure. Because the solute has artificially depressed the vapor pressure, far more thermal energy is required to push the pressure back up to match the atmosphere. The exact same logic applies to freezing point depression. Those identical solute particles physically interfere with the solvent molecules, requiring far colder temperatures to successfully lock the fluid into a rigid solid lattice. The sheer quantity of dissolved particles hijacks the solvent, forcing the liquid to require extreme temperatures to undergo standard phase transitions. The creation of an aqueous solution is the ultimate thermodynamic triumph of entropy over enthalpy. The specific chemical identity of the solute dictates exactly how much solid will dissolve, governed by the strict mathematical limits of the solubility product constant and the strategic presence of external ions. Yet once dissolved, those chemicals lose their unique identities, acting merely as anonymous physical disruptors that dictate exactly when the bulk fluid boils and freezes. These exact thermodynamic equations govern the precipitation of toxic heavy metals in groundwater and establish the critical osmotic pressures inside human cells. Mastering the mechanics of dissolution transforms an aqueous solution from a random mixture into a perfectly predictable, highly manipulable physical system.